This is Dr. Anthony Revis, and this is SVSU General Chemistry 111, Chapter 5, Lecture 2. Lecture 2 of Chapter 5. This chapter will cover 3 topics. It will cover energy basics, calorimetry, and enthalpy. These topics will be covered, but they might not be covered in this order. Let's begin with a review of some definitions. First, law of thermodynamics and the law of conservation of energy. The law of conservation of energy says that during a chemical or physical process, energy can be neither created nor destroyed, although it can be transformed. The first law says that if heat is recognized as a form of energy, then the total energy of a system plus its surroundings is conserved. In other words, you cannot destroy nor create energy. That is an important principle, that the energy of the universe remains constant. Some important definitions about the types of energy. First of all, energy is the capacity to do work. If work is done, it uses energy to do it. If energy is available, it can be used to do work. Some important definitions with regard to this particular lecture are that thermal energy is the energy associated with the random motion of atoms and molecules. That's what thermal energy is. It is associated with random motion of atoms and molecules. Molecules and atoms have motion, and thermal energy is how that motion is expressed. Chemical energy is the energy stored in chemical bonds. Compounds have bonds, therefore it has energy, and that's potential energy. So potential energy is the energy available by virtue of its position or its composition. It is energy at rest. Kinetic energy, however, is energy due to the movement of an object. An object in motion has kinetic energy. So in the rest of this lecture, in the rest of this chapter, we're going to solve some problems, thermochemical problems, that is, that will use certain key equations that involve energy and our understanding of energy, and to actually also teach concepts about thermodynamics and thermochemistry. We want to show you this particular slide with these definitions because these tend to be the ones that are most troublesome because of how they are defined. It's important that you learn the formal definition, but also be aware of the context in which these definitions are used. The key to being successful in using these equations will be paying attention to the units. I point that out because oftentimes from textbook to textbook and different textbooks will use a different notation for some of these. So I want to bring to attention the ones that we're going to use here, and they're the ones that are most often used. However, there is one that's used interchangeably, and oftentimes you'll find it within one book, a different notation. So these are definitions. Q equals ms delta T, Q equals m delta H, Q equals C delta T. S will stand for specific heat or specific heat capacity. Depending on the conversation you're in, or oftentimes whose textbook you read or with whom you're having a conversation, you'll hear specific heat, and others will say specific heat capacity. So be aware of that. Oftentimes you will hear the familiar jargon about these more than the formal definitions of these. But the way you will know it's talking about specific heat is by the units. Joules or some other unit such as kilojoules So you'll have joules per gram degree C. So be aware that when it comes to specific heat, or what's occasionally called the specific heat capacity, S will represent it. Okay? In some textbooks, C does. So be aware of that. Uppercase C will be used for heat capacity itself. And they sound alike, but you'll know the difference by the units. Again, I want to point this out. There are formal definitions and then there are informal usage of the terminology. Q stands for heat, which will be in joules or perhaps kilojoules, and occasionally you'll see kilocalories. Mass is going to be grams, then delta H is the enthalpy change, and delta T will be the change in temperature. But I really want to make you aware that occasionally you'll see S, lowercase s, and lowercase c used interchangeably. So when you see that, or if that happens to you, check the units is the key. The specific heat or specific heat capacity will be in joules per gram degree C. All right. We will give you a more formal definition of these as we go. All right. But I want to bring your attention that it's important to watch the units as you move forward. All right. So with that, let's start to understand some of the important features about the thermochemistry or thermochemical behavior of matter, of materials, gases, solid, liquids. We're going to start to learn that as we talk about heat and heat energy. And this slide shows you a summary of the concepts that we're going to use. Now, it is a bit unfair to introduce all of this to you at the beginning, but I think it's important to give you an idea of what to expect going forward. So let's walk through the types of things that you're going to see. So this is the prequel. This is a look at what you're going to see in the rest of this chapter. Okay? Now, when we talk about compositions of matter, or when we talk about actually the states of matter, we're going to focus on solids, liquids, and gases. The solids are shown here in area A, liquids in C, gases in E. What you're looking at here is the behavior of water. We're going to use water as our example. You're looking at the behavior of water as it goes from a solid to a gas. Okay, and that's what the climb in the curve represents. The climbing line where it goes up, then it goes horizontal, goes up, horizontal, and goes up again. This is the progression of water from being a solid, ice, to a gas that we often call steam. Okay? So, the very first phase, phase A, is what happens when temperature rises to the point where the ice melts. So we start at ice and the temperature goes up until it hits zero. We know that's the melting point of water, but essentially goes up to the melting point, whatever the material is. When it reaches the melting point, it then levels until all that material is melted, and once it's all melted, then there's another temperature rise, and when it gets there, it reaches the boiling point, and then that transition between liquid and gas, the temperature stays the same until it hits the point to where it's now all in the gas phase, and it goes up. Okay? So what you're looking at here are these transitions. So the first transition is warm or cools. The difference is the direction of the energy will be whether it's negative or positive. Then we have solids melt. So it stays at the same temperature until it's melted. Then it warms or cools. Okay? In the C area. And then in D, we have liquid vaporizes or the gas condenses until it's all there, and then it warms up again. Okay? So you're going to see in the rest of this chapter discussions about these types of events and how to calculate thermal heat and heat energy related to these types of transitions of materials. And in this case, we use water as the example when we talked about it, but you see the same type of curve for anything that can go from a solid to the gas state. As we work problems, you want to be aware of what state you're in. You want to know whether you're in a state of warming or cooling, because the calculation in that phase, in that state, is different. When there is warming or cooling, the energy will be related to the mass times the specific heat or specific heat capacity. You'll hear that term used. It's mass times specific heat times the change in the temperature. It is a change in temperature. We know that because the curve is going up. And that is what we see occurring in section A, section C, and section E. So if there's a temperature rise occurring, or temperature fall happening, we would use Q equals mass specific heat delta T. So when there's a temperature change, you want to think, I need the specific heat of that material. You get it? That's important. So in any of these calculations, as we move forward, if there's a temperature change, right away you want to remember that you need the specific heat, or what's called also the specific heat capacity. Now, when there is no temperature change, you simply need the mass times delta H of fusion, which involves the solid to liquid, or you need delta H vaporization, which involves the liquid to vapor or vapor to liquid. You either have the liquid vaporizing or the gas condensing. We see that in section D of our diagram. We see in section B where we have the solid melts or the liquid freezes. Again, the only difference, the value is going to be the same, the magnitude is going to be the same, except the direction of the flow, which determines the sign. Okay, so be aware of that. Okay. Now that I've introduced you to the concept and given you an overview of what to expect, let's start to talk now in more detail. Okay? Let's talk about energy and change of state. For a pure substance at its boiling point, the amount of heat added to boil the liquid is proportional to the mass of the liquid. So in other words, if you know the mass, that's proportional to the heat. The more mass, the more heat. The less mass, the less heat. That's what it means. So it's proportional. And the equation we use to do that is heat times its delta H of vaporization times its mass. Okay? Where Q equals the energy required to vaporize. M is the amount in moles or mass in grams. Okay? Choosing mass or moles depends on what the expectation is for the final answer. But if you have moles, you simply convert moles to mass. Okay? And that's how we typically will carry this out. We'll convert the moles to mass, and then we will carry out the calculation. So what's delta H of vaporization? Delta H of vaporization is the enthalpy of vaporization, or the heat of vaporization. Okay? It's an indication of the heat energy. And it's vaporization in this case because it is measuring what happens in going from the liquid to the gas or the gas to the liquid. And the only difference is the direction of the flow. It's either flowing from liquid to the gas or gas to the liquid. It's either going uphill or downhill. It's either being volatilized or condensed, evaporated or condensed. Okay? It's also the energy change when a vapor condenses to a liquid at a boiling point, and therefore it's called the heat of condensation. But typically you'll have it heat of vaporization, and that means it either vaporizes or it condensed. So if you know it's either going from gas to liquid or liquid to gas, that is delta H of vaporization. Those values are found in tables. So to be able to carry out one of these calculations, we simply have to be aware of the mass to complete the process. Now, there's also a heat of fusion, delta H of fusion. Delta H of fusion is the enthalpy or heat of fusion. Okay? It is the amount of energy released in freezing a sample and is exactly the same amount of energy used to melt that sample. The other term for this is heat of solidification. The values are the same, but the sign is changed to a negative, the direction of the flow. So the signs matter. Okay, the sign tells you the direction of the flow, either going again in the positive direction or the negative direction. Okay, so be aware of that. But the value, the size of the value is exactly the same. So there we have heat of vaporization. It deals with gas to liquid or liquid to gas, or we have heat of fusion, which is solid to liquid or liquid to solid. These values are used when there is no temperature change. So heat of vaporization, heat of fusion are used when there is no temperature rise or temperature fall. That's how we calculate the energy. And that energy is proportional to the mass. This table shows you some standard heats of fusion and heats of vaporization. We don't expect you to memorize this table. Be aware of it to use it. Note what the units are for the heat of fusion. They're joules per gram, or they will be in kilojoules per gram. So be aware of that. And they give you the boiling point of various materials. Water there at 100 degrees boiling point, 0 degrees freezing. So be aware of those. But you don't have to memorize them. Just know where to find the table. More times than not, you're given these values on exams. And remember, when you use these values, there are two equations for them. There is Q equals mass times the heat of fusion and mass times the heat of vaporization. These are the two formulas that you use when there is no temperature change. When there's a phase change only, it's either solid to liquid or liquid to solid, and that's fusion. If it's liquid to gas or gas to liquid, then that's heat of vaporization. When there is a temperature change within a state, either solid, liquid, gas, temperature rise or fall within a state, specific heat is used to determine the heat value. The specific heat of a substance, then, is the amount of heat, Q, required to raise the temperature of 1 gram of the substance by 1 degree Celsius. Specific heat is used when there is a temperature rise or fall. Specific heat values are established for many materials. We show you examples in the table here on this slide, table 6.2. The units are very important. The units here are joules per gram degrees C. So, when we have to carry out a calculation involving heat, where there is a temperature change, Q equals mass times specific heat, or you will hear the term specific heat capacity, times delta T. And this T can be a uppercase T or lowercase t, it doesn't matter. Delta T equals T final minus T initial. That is the equation, again, that we use when there is a temperature change. Heat is proportional to the mass times the specific heat of the material times the temperature rise or fall, the delta between the rise or fall. So now you have that equation, and you also have the equation for where there is no temperature change. And values for any of these equations can be found on tables. For example, table 15.5 shows the specific heat values of some materials. So these are standards. These are given to you when you have problems to work. So let's start to work some problems to reinforce what it is we've already learned. As you work through these problems, it is helpful if you think of each of the phases or each of the steps as an individual problem. So it's important again that you treat each step, each phase as an individual problem. All right, so let's get going with working a problem. And we're going to dive right in with a problem that involves going across each of the phases and examining each of the temperature rises. So we're going to have 3 temperature rises and 2 phase changes. Now, I show you this because if you can work the entire spectrum, then the individual steps are much easier. So we're going to treat this as a different problem for each step, each transition, each phase change. In doing so, you will know how to work problems for the individual steps or phases. Here's the problem. Calculate the total heat transferred when 19.6 grams of ice, which is frozen water, that is initially at minus 12 C, is heated to steam at 115 degrees C. So we're going to go from solid, we're going to raise the temperature, we're going to melt the solid, we're going to raise the temperature as a liquid, we're going to transition that liquid to the gas phase, vaporize it, boil it, and then we're going to heat it in the gas phase. And we're going to treat each step in this as a different problem. And then we will take the sum of this entire transition. So let's start with the first problem. Let's deal with going from A to B, which is we're going to raise the temperature of the solid. So, since there's a temperature change involved, we know that our equation is Q equals ms delta T. Anytime there is a temperature rise or fall, we must have the specific heat or the specific heat capacity of the material. In this case, water. So to do that, we simply plug the values in. And that is what you'll do over and over again. Determine where you are in the transition. Is it a transition from solid to liquid, liquid to gas, or is it a temperature rise within a particular phase? So let's go from A to B. We use ms times delta T. We basically plug in the values. We look at the values, put them in. Specific heat of water is 2.06 joule per gram degrees C. We calculate our temperature. We have the final minus the initial. And then we convert the final answer to kilojoules. So the last conversion factor in this equation is a conversion from joules to kilojoules. That is the type of conversion we will expect you to be capable of doing at this point. Okay? So once we run the numbers, we get 0.48036 figs kilojoules. That completes one of the problems. And the goal of that problem was to take ice from -12 to 0, because 0 is the point where it melts and becomes a liquid. So when you have these type of problems, you take it from where the temperature is to the next phase change of the material, of the liquid. So next we will work our second problem. And the goal here is to consider what happens within the liquid phase of the water, where the heat of fusion is involved in going from solid to liquid or liquid to solid. In this case, we have no temperature change. The equation is Q equals M times delta H of fusion. We look on the table and get the delta H of fusion. We know that we have 19.6 grams. We put it in the equation and we convert this to kilojoules as well, using a standard conversion factor of 1 kilojoule per 1,000 joules, and we set it up according to the dimension analysis and the rules of math. When we calculate this through, our second problem is done. In the transition of B to C, we obtain 6.53 kilojoules. Our third problem will be to deal with another temperature change, a temperature rise. In this case, we will go from 0 to 100 degrees C, which is the boiling point of water. It is a point at which it moves from a liquid to a vapor. Because there's a temperature change, we use the equation Ms times delta T. We put these values in using the same mass, because the mass did not change. We put in the specific heat now of water as water liquid. The earlier specific heat was water as ice. Here we have water as liquid. We put in the values, we do the conversion factor, and we obtain 8.19 kilojoules, 36 figs. That completes problem number 3, or the third phase of this transition. The fourth problem that we do is B to C. There's a phase change, liquid to vapor. Since there's a phase change, liquid to vapor, we use the heat of vaporization times the mass. And as it turns out, this heat of vaporization is already in kilojoules. Therefore, we now have 44.3 kilojoules. So, one of the things you have to pay attention to is the units and when to convert everything now to joules or kilojoules. In this case, we made the conversions to kilojoules. And so for the phase change, liquid to vapor, we have 44.3 kilojoules, 3 sig figs. Now we move on to the final phase, the E to F. A temperature change, it's evaporation happening. We're going to see a rise in temperature. Therefore, Q equals M times S times delta T. Note we're using two general equations over and over again, depending on where we are in this entire transition. We plug in the values. In this case, we need a specific heat for when it is steam or gas. We need to go from 100 degrees C to 115 degrees C. So it's 115 minus 100 degrees C. We do a conversion factor to get to kilojoules, and we obtain 0.590 kilojoules. Now that we have values from each of the stages in the process, we add them together. It is that straightforward. So again, you treat each of the transitions, each of the points along the transition, as a separate problem, individual problems, and then add them together for a final answer. Our final answer is 60.1 kilojoules. Not all problems will take you across all the phases. Let's take an example of ethanol. Calculate the total heat in joules needed to convert 15.0 grams of liquid ethanol at 25 degrees C to gas at its boiling point of 78.0 degrees C. The specific heat of ethanol is 2.46 joule per gram degrees C. The heat of vaporization for liquid ethanol is 841 joule per gram. So we show you a diagram of what that will look like. You have the first phase is the liquid phase, then the second phase is the gas to liquid phase. So your liquid vaporizes or the gas condenses at that phase, which means that is a heat of vaporization. So we could calculate that with Q equals M times delta HV. Then we have phase 1 where it's liquid, warms or cools, therefore there's a heat change, and we will use MS delta T. So we will treat this like two different problems. We note that our delta T that we need will involve 78.0 degrees C minus 25 degrees C, which gives us a delta T of 53.0 C. So we have that value and we have it set aside. In the first phase, we note that we use Q equals MS delta T because there's a temperature change. We put in the values. So we multiply the 15.0 grams times the specific heat of ethanol, which we found on the table, times the delta T. We obtain 1,960 joules. We do step 2 in this process, which involves a phase change, no temperature. Therefore, it's Q equals M delta H, and this delta H is delta H of fusion. And so we look that up on a table, we put it into the equation, we calculate the values shown here. We then take the two values obtained, we sum them, and we have a total heat that's needed for this process. We can use these formulas and this process to evaluate a number of heat of reaction problems. Let's take an example shown here. A quantity of 1.00 times 10 to the 2 mils of 0.500 molar HCl was mixed with 1.00 times 10 to the 2 mils. So essentially you have 100 mils mixed with 100 mils of the same molar concentration of an acid and a base. This is a neutralization reaction. So it's done in a constant pressure calorimeter. And note that in this constant pressure calorimeter, the heat capacity is negligible, and that's important. So what is a constant pressure calorimeter, and what does it mean when it talks about the heat capacity? Take a look at the equations on the right bottom of this slide, and you will see what we mean. In a constant pressure calorimeter, the heat of the system equals the water plus the heat of the calorimeter plus the reaction. The calorimeter is essentially an insulated vessel. It's a styrofoam cup with a thermometer in it where you put water. That's essentially what it is. And Q system in this case equals 0. So if we work through the math, what we find is that the heat of the water equals the mass times the specific heat of the substance. In this case, it would be the specific heat of the two materials we added times delta T. And what we also know in thermochemistry is that the heat capacity, which you will learn more about in slides to come, is equal to the mass times the specific heat. And therefore, we can place in a heat capacity factor here as well. However, in this problem, since we have mass, we have specific heat, we'll be able to use it. Okay? So it's important to note that there are two approaches to this. One, with a known calorimeter value, we can put in that for the heat capacity, or we can solve this problem by using the mass times the specific heat. So, we know that the initial temperature of the HCl and sodium hydroxide was the same, and the final temperature of the mixture was the same. So we need to calculate the heat change of neutralization of this reaction. And once we get that, we want to do it on a molar basis. So, another example, don't try to work the problem in one step. Treat the neutralization as a reaction, get its value, and then treat that value as a separate problem to determine the molar quantity. That is the per mole heat. So we assume that the density and the specific heat of the solution are the same as water. That is an important assumption. So since we assume that, we can look on a table and we can get both those values. And that is a reasonable assumption. It is a good first approximation. So then we'll assume that no heat is lost to the surroundings. Therefore, the heat of the system equals the solution plus the reaction. When that adds up, it should sum out to 0. In other words, we cannot lose heat nor gain heat. Okay? The heat should be equal. The reaction is positive, the solution will be negative. All right? So that is the heat absorbed by the combined solution. That is the heat of solution. Because the density of the solution is 1, the mass is 100 mils solution for each of these. Okay? So, those are good first approximations. And these first approximations are good enough for this level of study. So let's put it all together. We're going to work this as if it were two problems. First, we're going to find the heat, and then we're going to see what that heat is on a per mole basis. So, we plug in the values that we have. The mass should be twice the materials that we have, the sodium hydroxide plus the HCl. Don't forget to do that step. It is the total mass times the specific heat, and we're using specific heat of water, times delta T, which is the final temperature minus the initial temp. We calculate these values, and what we find is 2.81 kilojoules. However, we're dealing with the heat of the reaction, therefore it's going to be minus the heat of the solution. So if the solution had a positive value, which it does, then the heat of reaction is negative. And what this tells us is that this is an exothermic reaction. It is exothermic because it has a negative value. If I wrote this value in the balanced equation, it will look like this, with the 2.81 kilojoules written on the right side of the equation. So now the second part of this question, which is our second problem, and we treat it as two separate problems, is to determine the number of moles, so that we can take the kilojoules and divide it by the number of moles to determine the kilojoules per mole. And keep in mind the value will be negative because it's exothermic. So from the molarities, we can do a dimensional analysis, take the number of mils to convert it to the moles by using the molarity value, and we show you that calculation here. And that gives us the number of moles. We take those moles as the denominator, the kilojoules, and we will obtain a minus 56.2 kilojoules per mole. Several of the standard or well-known reactions, the heats of reaction can be found on tables or in tables. And we show you some examples here. And you note the HCl plus sodium hydroxide neutralization is shown here at 56.2 kilojoules per mole. Let's work another problem that involves constant pressure. A lead pellet having a mass of 26.47 grams at 89.98 degrees C. You now know what that device looks like, and it had again negligible heat capacity. It contained 100 mils of water. The water temperature rose from 25.50 degrees C to 23.17 degrees C. What is the specific heat of the lead pellet? So in this case, we're able to calculate the specific heat. At least that is our target. Okay? We use the same equations that we've used before. We note that lead plus water equals 0. Therefore, lead is going to be minus the heat of water. We know how to calculate the heat of water because we know the calorimeter value for water. And when we don't know the calorimeter value for water, we simply use the mass times specific heat, which we do know. Okay? So we show you a diagram here of what's happening initially, and then we show you what it looks like finally. So this is how we think through the problem. So let's go through. We basically put in the values, and so we add in 100 grams, the specific heat of water, 4.184 joule per gram degrees C. We calculate our delta T, and we obtain a heat for water of 280.3 joules. Note, however, that that's going to be the opposite for the heat of lead. So essentially we have the lead at minus 280.3 joules. Now, we would then take that value and use this same equation for lead, where S, specific heat, is the unknown variable. We put in the units, we do the standard math by rearranging the equation, or we put it in and run the rest of the values on our calculator, and we obtain a specific heat. After we put in the equation, we obtain a value for the specific heat of 0.158 joule per gram degrees C. So we worked the problem with the constant pressure. Let's do a problem with constant volume. The principles are the same. In this case, we are going to use the heat capacity. So what is heat capacity? Heat capacity of an object or substance is independent of the amount of mass. This value, the heat capacity, is different from the specific heat or specific heat capacity because specific heat capacity depends on mass. So essentially, the heat capacity is mass times the specific heat. Mass times specific heat gives us the heat capacity. So we can take this equation and plug in the heat capacity where we don't have the mass or the specific heat. The calorimeters are designed with knowing the heat capacity in mind. Again, note the units, very important. The units of the heat capacity, joules per degree C. The specific heat is joules per gram degrees C. And we show you a typical calorimeter here. Again, it's a device that allows you to carry out the chemistry in a controlled environment, in a controlled system. In this case, where the volume is controlled. So let's work a problem. A quantity of 1.435 grams of naphthalene was burned in a constant volume calorimeter. the temperature of the water went from 20.28 degrees C to 25.95 degrees. If we know the heat capacity of the device at 10.17 kilojoules per degree C, we can calculate on a molar basis the combustion of this process, of this reaction. So we'll use the equation Q equals heat capacity times delta T. We take the heat capacity of the calorimeter and we put it in. We then calculate delta T and we obtain 57.66 kilojoules. However, we know that the heat of the system equals the calorimeter plus the reaction, and that has to equal 0. Therefore, the heat of the calorimeter is minus the heat of reaction. So essentially our heat of reaction is the opposite sign of what we obtained at minus 57.66 kilojoules. So now we can take this value and we can treat it as a dimensional analysis problem to obtain the per molar basis. So what do? We know that 57.66 kilojoules were produced from 1.435 grams. We can then take those grams and we can convert that to moles. And that's essentially what we're doing. You could do this in 2 steps. Simply convert the grams to moles and then divide the heat by the moles. We simply set it up as one-dimensional analysis problem. But you could have done this in 2 steps, would have been perfectly acceptable. And in fact, I would almost advise that you calculate the moles and then you set it up. It is not always common to set up energy per gram. We only did that to demonstrate to you that if you do understand what the proper ratios and relationships are, you can proceed to do that. But be cautioned, there are some ratios that are not allowed. So the preferred way would be to take your 1.435 grams, convert it to moles, then divide the heat by the number of moles. If you choose to do it the way we show you here, be aware that your dimensional analysis units in math must work out properly. So let's recap. In working through problems involving temperature and heat energy, we work them by working through each of the transitions. There is a transition wherein temperature rises or falls. That can happen in the solid going to liquid. It can happen in the liquid going to vapor, and it can happen in the vapor phase. Solid, liquid, gas phases will involve or can involve temperature changes. When there is a phase change, we do not use delta T equations. We use heat of fusion when it's a solid to liquid. We use heat of vaporization when it's liquid to gas. When the problem involves more than one phase or more than one transition or more than one event, we then take each event as an individual problem and we sum them at the end. If we need to determine that on a per mole basis, we then take values that would help us get to a molar value, and we divide our heat by the moles. So that completes Lecture 2 of Chapter 5, Thermal Chemistry. Again, Lecture 2, Chapter 5.